Good morning, everybody. The first presentation is a very short introduction to maybe the more boring stuff like who are we? We want a little bit the institutional context as well, to understand a little bit what CGIAR is. Not everybody knows everything about the CGIAR, not even us, because there is also a change process. A little bit explaining what is going on in the CGIAR, who we are. So I'm the research director for the digital inclusion lever, and there's several people of the team here in the room. Maybe it's nice to stand up so that everybody can see who we are. So Danielle, there's David, Elizabeth. You can also stand up. Yeah. So these are the visitors, so to say, coming today to for the seminar. We also have a group based here in Montpellier. So Elizabeth is based in Montpellier. Is a little bit based in Montpellier. It's close, and I'll be here working from next summer onwards. I will also be based here, and hopefully growing the team a bit in Montpellier. But most of the people are either in Latin America, Africa, and Asia. The largest groups are based in Cali, Colombia, and Hanoi, Vietnam at the moment. And we have a growing group also in Arusha, Tanzania, and a number of other places as well. So, so my name is Jacob van Etten. I'm originally from the Netherlands, but I've worked for a long time especially in Latin America, but also a bit in Africa and Asia. Moving more and more into digital topics, starting more with a kind of a crop science and social science starting point. And working mostly on things around crowdsourcing, citizen science, these types of topics. And now leading the digital inclusion lever. So it's called digital inclusion because the social aspect of it is also very important. So we combine in the group a lot of digital and also social sciences, all around agriculture and natural resource management. So first, kind of maybe the more boring stuff. Who are we in terms of institutions, etc. So we have the CGIAR, which is a combination of several institutes. There has been some change. Some institutes have left recently or are not part of the one CG process. Then within that, there is the Alliance of Bioversity International and CIAT, which were previously two separate institutes that have come together. It's now one of the largest CGIAR centers. One out of, I think we have 11 right now because of all these changes. We were 15 originally. And then within the Alliance, we are part of this called the Digital Inclusion Research Area, or lever. We talk about levers because we have a strategy that looks at the whole food system and then looks at different levers for change, basically. And we see digital inclusion as one of the main levers for change in food systems. So this is so the Alliance of Bioversity International and CIAT. Bioversity here in Montpellier. We have had a long presence here, starting with the presence of INIBA, the Banana Research Institute, and then which became part of Bioversity. So there's been long presence here in Montpellier and linkages also to the French research system through especially Bioversity. But now it's one big institute. So Elizabeth Arnaud, who's here, is witness of that, has been working from here for a long time in Montpellier for Bioversity, and originally INIBAP, I think, right? Yeah, when you started. Yeah. Okay, so when Bioversity and CIAT came together 3 years ago as one institute, because there's many complementarities, and also to basically to save costs as well. Like we have two boards and all these differences, whereas actually we have very similar missions. So we came together and created one strategy. So I was saying before, it's about these levers of change in food systems. So we have these 6 areas where we look at different levers of change in food systems. And as you can see, digital inclusion was really put at the highest level in terms of the strategy in the Institute. It was quite new in the CGIAR because we have this long tradition of working mainly on breeding, starting in the 1960s. But now digital inclusion is really one of the main areas within the Alliance. then one CGIAR, that's one level up, right? So the Alliance of Bioversity and CIAT is part of the CGIAR. And also in the CGIAR, there's this change process going on, where also the governance is unified. So we had like 15 institutes with 15 different boards and a lot of overhead, so to say. The idea is that should all come together in a much more efficient system. Also, many of these institutes were kind of competing for the same funds, right? Instead of collaborating, they would each write a different grant to, say, the German government, and would compete for funding rather than actually collaborating. So all of that is now changing. So we have a lot of common initiatives. It's been a long change process, but this time the change is a bit more radical in the sense that there will be one board and one big structure for the CGIAR. So in this, and that is also part of a history of the CGIAR in terms of diversification. As I said, we started in the 60s with breeding, basically working on rice, wheat, and maize, the green revolution crops originally. But from that, our mission has been like broadening to encompass not only agriculture, but actually the entire food system. Right now working on all these other topics. So starting with rice, wheat, maize, we now work on climate adaptation and mitigation, poverty reduction, nutrition, health, and food security. You see the whole food system comes into the picture. Environmental health and biodiversity, so not only agriculture there as well. And also gender equity, youth, and social inclusion in rural livelihoods as well. So this is the new structure. I don't want to say too much about it, but here you see the group that I'm leading is part of what we call systems transformation, which is kind of across. But this is so to say almost like agronomy, traditional agronomy, and this is breeding basically. We are basically in an area which looks at the whole system. So we also look at other topics within food systems, so not only production, but also some other topics. And actually this morning we'll also be talking about food trade, for example, and not only agronomy. So that is also for us a little bit one of the new challenges, to really move into the whole food system approach and not stick with production only. And that's also why we found it important to talk a little bit about that with you as well, because I think we have the same challenges in that area, right? So this is the group, the leaders of the group of the digital inclusion lever within the Alliance of CIAT Bioversity within the CG. Some of the people are in the room. David is here, Elizabeth is here, and Danielle is here in the front row. And we have these different teams. So we have, let's start with this group. So we have a group that looks at digital solution development. So really the back end stuff, in terms of getting order in the house for digital solution development, being much more efficient in that. For example, in repurposing existing code, not everybody building different frameworks, etc. Working on data standardization and ontologies, and good practices in programming as well. Researchers are typically very bad at like we write a script and that's it. This team brings in a really like a software engineering perspective into the work that we do. Then let's go with this one. So this David has just joined the team, leading a large project called Artemis, which is looking at a really new approach of phenotyping using tools that are appropriate in resource-poor contexts. So the phenomics has been evolving very quickly in terms of using drones, using also vehicles, what are called rovers, for example. But many of these technologies are really limiting in conditions of breeding programs, for example, in Africa. But mobile phones and mobile phone technology is really has a high potential in this area and could be used in these more resource-poor contexts. So what David's job is in this project is actually to take all the learning that there's been working with drones and working with rovers, etc., in kind of field phenotyping, to much cheaper platforms that can be deployed in much more resource-limited conditions. Then we have a team that's looking at data-driven sustainability. Tiffany Talsma and Louis is also here in the room in the back, using digital technologies to look at how corporate businesses, especially, can monitor the impacts of their business. So, working, for example, with the cocoa industry in Ghana, looking at the impact of cocoa on deforestation or habitat change in general. And building that into the whole into the value chain, so that the information flows, working with the communities as well in Ghana on ecosystem services and payment for ecosystem services, for example, and building digital tools into this, also using things like remote sensing, basically showing to corporate business that it's doable. It can be simplified in such a way that it actually becomes doable for them to do it. And it's not like an unreachable goal to actually use digital tools for sustainability management in these value chains. Then Danielle is working on digital transformation of agri-food systems especially looking at things like digital agronomy, I would say, and extension services. How should the extension agent of the future look like? Of course, Danielle will be talking about this, so I won't say much more about it. And there's here is the logo, digital innovation and transformation. So Danielle is also, just a reminder for me, Danielle is also the focal point for the one of the CGIAR wide initiatives on digital innovation and transformation, where he also leads one of the work packages looking precisely at digital transformation of agri-food systems. Just as a reminder, so we are also involved. So even in this big scheme of the CG that I showed before, this one, we are just in one box, right here. But in reality, I should have. What do I do now, right? This. Yeah. Should be okay now. We're also linked to a lot of the other parts of the system, right? Actually, you look at this and for some reason, people always design it as a hierarchy, but in reality, it's a network, right? So we're working with phenotyping, we're working with breeding groups here, for example. We're working with some of the stuff that we do in biodiversity, we're working with groups here. And also within this group, we're working with several groups. So we see ourselves, even more than any of the other groups, we see ourselves a little bit as a spider in a web rather than just being one little cog in a big machine, so to speak. So I think the only one that I guarded for the last, and the one that is really, I think, now causing some waves in the CGIAR is the group that is led by Anna Müller, who's here, about inclusive design and user research. So in a lot of the work that we did, many times we started from a kind of a technical point of view, right? So we want to improve something in breeding, or we want to work on remote sensing and sustainability and habitat change, etc. And the kind of the user perspective comes at in the last stage of the design process. But over the last years, we've really learned to that's not how it's done, a proper design process. Anna's task is to really bring in this kind of user research perspective in a lot of the work that we've done. And I think some of the most successful work that we've done has been really good at doing this, bringing in user-centered design and things like this. And also on top of that, the inclusion element, right? So things like gender and social heterogeneity, how do we bring that in? How do we design not only for like the best users, because we want everybody to do like the most sophisticated things, but actually to look at also resource limited users that have challenges. And there's very exciting research on that. Also in European context, right? There's a lot of very interesting research about how, for example, elderly people use technologies and make very interesting uses of technologies for communication with their children, etc. In our societies, which are rapidly growing older, right? And so this whole area is actually a very exciting area is also for digital design, leading a very interesting initiative, and also having a lot of success in the rest of the CGIAR in bringing this perspective to the table and becoming part of other types of research. So we're going to talk in the next little talks about a lot of the work that we do, what is going on, because that's maybe the most interesting touch points to work with DigitAg on what we're going to do in the future, not what we've done in the past. But I want to show a few things that are really like mature products, very briefly, just mentioning them. And then also talking a little bit about what we want to do with those. Then in the next talks, we're going to talk also about like more ongoing, less mature things as well. So one of the products that we've developed over the last years is a platform called Klimop. And this, we've talked about it in the DigitAg conference about on-farm testing, actually, where I had a little talk about this one. It's a keynote. This is about farming testing of agricultural technologies through a citizen science approach. And later on, we'll also have a talk where I also elaborate this a little bit more. This is a really mature platform now that is being used by many of the breeding programs within the CGIAR and national breeding institutes to test especially varieties, but now also starting to work more on agronomic techniques to test them. So this is now in a scaling phase. Another mature product is Terra-I or Terra-I Plus, because there's things added to it all the time. So this is the work that we're doing around sustainability monitoring, and this is a platform also used in production by organizations to look at habitat change and other areas of sustainability monitoring. So this is the work of Reymondin, and we'll also be talking a little bit more about this. Another mature product where we're getting a version 2.0, right, Daniel, is APS, which is about digital agricultural agronomy and extension, which makes two-way data flow work in agronomy, where the input can be very diverse, so kind of dirty data, so to say, or data that, for example, agricultural, like farmers organizations already have, but cleaning a lot of that information, but also incorporating other information, images, voice, using artificial intelligence to inform decision-making. So this is work that is also now in a kind of a scaling phase. We have recently approved, or actually today we're starting, today we're starting a very big project in Colombia to scale this, right? And Daniel will talk about this, yeah. But actually today we're starting this project. I just remembered, I mean, just had last week a visit from the Minister of Agriculture of Colombia to our campus in Cali, Colombia, also celebrating this. Another kind of mature product that has been developed for the government of Guatemala is a system to do food security monitoring with very simple indicators at community level, but building up into a national system. Where also now we're working towards kind of a scaling and expansion of this in Guatemala with the digital CGIAR initiative in Guatemala and beyond. So we've done all this work over the last, say, 10 years to build all these different products, many times in teams that were not very well connected, so to say. Well, for example, because we were in different organizations, right? Some people were in CIAT, other people in Bioversity, more competing than collaborating sometimes. So one of the challenges that we would like to face now as well and really address is, how do we build this into a digital innovation ecosystem, right? How do we no longer just build individual products, but build it up into a digital innovation ecosystem? This is how I want to close this little talk, to say something about this. So one thing that should be possible, and it's maybe one of the first steps, is how can these different products start talking to each other, right? So that is things about data standardization, APIs, and making different applications talk to each other. That is about good programming, good software engineering, going beyond what researchers usually do, very focused on say, the statistical bits and the machine learning and this and that, but also looking much more at the sustainability of the software. So that these different systems can start to talk with each other. Maybe not all tools with all tools, right? But there could be interesting combinations where if you have a tool, for example, this is a tool that looks at diseases with image recognition. What if those data can be fed into our digital agronomy platform? That should be possible. So that kind of work is needed. We're doing quite a bit of that already now. But that then should lead to this kind of interoperable system that work well together and can exchange data. So, but that's not the only thing that we need, right? That's only like a first step. The next step is, how do we make it possible for others to be using our tools much more than they do now? So organizations outside of our research sphere, we cannot bombard them with tools, like with 10 different tools, right? If you're a farm organization, say in Colombia, even if we go and say, look, we have 10 tools for you, very difficult, right? So we should have mechanisms in which they can combine different tools. They look as maybe as one tool to them, right? And but they can do that quickly. So they don't need to develop those tools separately or combine them from different vendors, etc. They should be able to use a lot of the open source code that we have, etc., but build them quickly, benefiting from, say, the standardization that are already part of your tools. And there's also, we're not the only ones working on this. So there's also, for example, in the Linux Foundation, a project called Xstack that is doing a lot of this. So say in 10 years from now, it should be possible to build an application that took us 10 years to build that in, say, a few months using existing tools. Yeah, because we're doing a lot of work separately in different teams that everybody's doing. Everybody is building something where you take data in the field, you put it into a database. Why should everybody be doing that separately? And then the next step is also supporting these organizations and actually, so these kinds of things, bundling that as services to farmers. Farmers, same thing. They cannot work with 10 tools either, right? How do you bundle this? How do you bring things together? How can you bundle, say, an insurance product, a risk management monitoring product, and credit, for example, in one product for a farmer that they can sign up to, maybe some digital extension as well. That's the work here. We also need to support. So actually in the Colombian project, that will be a big part of the work as well. And then of course, the next step is the actual users. In this case, farmers, but also other users, decision makers at different levels in farm organizations, in organizations that provide services to farmers, which then also should have fewer but better integrated services to reach these different needs. And of course, in the end, and this is like the end game of all of this, of all the work that we do, is how can people make better decisions, right? And we need all of this to get here, right? A lot of what we did was kind of shortcut, right? To think this doesn't exist, and we are going with this one directly to a farmer. That is not possible if we really want to scale, right? If we want to reach millions of farmers with digital products, we always say that is possible in principle. It doesn't mean we can just shortcut, right? We need to build this kind of digital innovation system so that when we develop something here, we can actually take it from here to here and then to here, right? And not bother a single farmer with one scientific product. So this, to us, is one of the main challenges of what we're doing now. We're doing quite a bit of this already, but doing this much more systematically, also in partnership with others. So I already mentioned Xstack, but also, of course, DigitAg and others. For example, working with the breeding programs, who also have their software, working with digital extension organizations to take care also of the delivery, working together on standards, seeing ourselves also as being part of a bigger digital ecosystem. All of that is part of the vision that we are developing. So that's it for now. Thank you very much.
So good morning to everyone. And thank you, Jacob, for the introductions. I'm Daniel Jiménez. I'm one of the scientists working for the CGIAR on digital agriculture. And I've been working for more than 15 years on topics related to digital agriculture, including data-driven agronomy, digital extension, big data, site-specific agriculture, and everything, pretty much everything related to the digital transformation of agri-food systems. And the idea today is to share with you, do I have the presentation here? Just click. Oh, good. I'll see to take about, of the keyboard and this nice screen. Let's see how it goes. So the idea is to share with you, like Jacob was mentioning, we're really excited about this project that is starting today. So this is part of the project. The project is called Digital Agriculture and Climate Services for the modernization of agriculture extension services in Colombia, where we want to keep supporting Colombia in the initiatives related to climate smart and digital related topics. And I say keep helping and keep supporting Colombia because this project builds on a previous pilot that we implemented over the period of time of 2013 and 2016. And we got some outputs and findings that support the agricultural sector in Colombia. Like we co-develop with the partners platforms in order to collect information, analyze information, and disseminate and share information. We co-develop that with several of our partners and crop sectors in Colombia. We also, through data mining approaches, we could determine what were the most limiting factors for a wide variety of crops across the country. And for example, we could determine how the varieties, what were the most limiting factors across the country for given varieties in specific regions. And that became like information that was then was embedded into the breeding programs. So we were basically talking that before it used to take to breeders 4 or 5 years to release a variety. And with this information, we were helping the breeders to accelerate the process to 2 or 3 years. So we also supported like the rice sector, for example, to understand much better what should be the planting dates, what should be growing, what should be the crop management to be implemented in the field, which varieties are more resilient to climate change. And based on that, so when the project finished in 2016, so we came all together and we start to work with the different crop sectors and actors that were involved in this project. And in 2017, we had different meetings to talk about what we should be presented to the Green Climate Fund, because the Colombian minister, the Minister of Agriculture and Rural Development in Colombia, we couldn't get money from them in order to keep contributing to this idea. So we submitted a proposal in 2018 to the Green Climate Fund. And since then, hundreds of meetings over the last 2 years. There's been a lot of back and forth. And to be honest, like some colleagues and myself, we felt like we went over the dissertations again, because there were so many filters in order to get this proposal approved. So finally, early this year in March, we got the approval of the project. But as you can see, it's a project of, oh, it didn't work. Oh, now it's working. Look, it's almost $100 million project that is going to be implemented in one country. So that's why Jacob and I are so excited about it, because we will have the opportunity to, many of the dreams that it probably can come true through this project in the topic of digital extension and agriculture. Oh. Thank you so much. So, but this project is not only about digital agriculture. To give you just one context, digital agriculture is one of the components. The other component is, obviously, we have this history of developing varieties. So we also are going to keep supporting the the country with varieties that are more resilient. And there are some lessons learned from the pilot, like, for example, in terms of monitoring and evaluation, we haven't considered actually the monitoring evaluation as serious as we should in that period of time, in that pilot. So we're now working a lot on knowledge management, on monitoring and evaluation, integrating into the project the angles of gender and inclusivity. Actually, Luis Armando Munoz, who is right there, he's the one leading this component of the project. But in order to, the idea as we're talking about digital agriculture in this space, so I'm going to we're going to get like a deep dive on this, on digital agriculture. So, in terms of the activities, we're basically integrating what is the modernization of agricultural extension, and coupled with the design of something that we have developed too, which is the climate information services. So we have the component of digital agriculture is in 2 axes. And we have the activities are based on the things that we have done in the project. So in the previous project, in the pilot, so we're going to scale many of those activities that we have done with the different crop sectors in Colombia, but we're also innovating with others. I mean, if what I mean here is like if we finish the project in 2016, so since 2016, there's been in the digital ecosystem, digital space, there are some projects, some advances and some tools that have been developed that we didn't use in the pilot. So that's why we also are including, for example, the human-centered design principles that Jacob was talking about, many things on remote sensing. Like one of the crops we work in is potato. And at the time in potato, remote sensing was kind of problematic because we couldn't deal with clouds. So now we have different satellite missions that could deal with clouds. So that's why we are innovating with the different tools that have been developed since 2016. We're working with different crops, rice, 8 crops, rice, sugarcane, coffee, livestock, maize, banana, and potato. And as you can see, we're basically covering pretty much the geography of the country, and it's very ambitious in terms of the impacts because we committed to benefit about 126,000 farmers in the country. In terms of the technologies to be employed, as I was saying, like some of them are tools that, you know, in 2016 were already like a cutting edge technologies, but we are introducing new technologies to characterize, for example, the environmental conditions of the farms. But we also, depending on the sector, depending on the crop, some of them have, for example, already information collected on crop management, on climate. But with some of them, we should start from the early beginning to co-develop those tools. So in terms of capture, that would be again like a co-development working with them. In terms of analytics, like, yes, in the pilot, we use data mining approaches, statistical models, machine learning, but for example, we haven't used deep learning. So in this phase, we're going to deep dive on deep learning and the identification of pests and diseases and create early warning systems, which we didn't do it in the first pilot. We will again use like a combination of process-based models, not that I read this here, and machine learning, because at the time, we didn't have like a lot of experience like combining both of them. But now we acquired some experience also on how to work with both of them. And this is very important because Jacob was mentioning that it became like very important to follow the principles of human-centered design or user research. So like when we went through all these filters for this project, this aspect came like as something that is very relevant. Because many of the questions that we've been asked is like, okay, but you're talking about digital in the developing world, but there's no internet, there's no literate capacities. So what are you going to do about? And this is human-centered design is like something that fits pretty well with this because it's how to take into account not only the environmental conditions of the farms, but also the socioeconomic context and how we should develop tools that are more targeted for those for the different populations that we have across the country, right? Like if they don't have internet and the level of literacy is low, which will be the tool that we should target that specific community in a given particular place. In terms of the team, so we are 34 researchers working on this and from different nationalities. And like since 2018, Elizabeth, can you remind me when you organized the event here on 2018? 18. So since Elizabeth organized the event here in Montpellier, we start to interact with our French colleagues from CIAT and other institutions. Sorry, Elizabeth? with our French colleagues and how to cooperate. And since then, we applied to internships. We wrote proposals together. We even some positions were advertised. We applied to some of them. And those efforts have like two things in common. One of them is that we were shortlisted in many of them, but we didn't get any. And the second one is that Emil and I, Emil, who's just sitting in the back right there, we were involved in all of them. So last year, we started to talk with Emil and see, you know, with his experience, how he can contribute to the project. So we included Emil. So we hope that Emil can join the team early next year. We're still trying to see when. And that would be like the first step to collaborate with you guys, like with the French institutions. We hope that really Emil can bring all his experience, not only in potato and remote sensing, human-centered design, but all the experience that he has acquired working in West Africa. So that will be the first step of the cooperation with France. But we also need, like, what we want is, like, it shouldn't stop there, right? Like, only with the mill, but to see if what other questions could be addressed, taking into account all the experience that you guys have here in France. I have to say that I was talking to Veronique, actually, that it's not very common to see like such a strong math background as engineers, like you guys in France, because we had the opportunity to have in the team like French engineers being part of the team and see how solid are in these topics that is not very common to see in all the geographies. Like to see that you can have agronomists with a pretty strong background in mathematics that can understand all these modeling techniques and the aspects related to when it comes to modeling, how important is to understand mathematics and but also have like this sense of communicate with people and to create tools that could be usable, could be easily understandable for the technicians, for example. So Jacob was talking about, you know, like how we develop different approaches, but sometimes they don't talk each other. We are still suffering of that. So now we can see, for example, across the organization that we have developed chatbots. So a chatbot to provide information on how the next season would look like in terms of climate. Chatbots to help us to understand the dynamics of different crops in different regions, but they don't talk each other. And we developed like different ways of doing, like sending IVR messages, SMS, USSD, radio, etc. Right? So for us and for the project, that would be like we kind of missing an opportunity to see how can we collect all this information, because this is not only sending information, but sending information to farmers, but it's also collecting information of, for example, what is happening in one particular place in a specific period of time, which from an AI modeling perspective will be like examples to train a model to understand better what is working, what is not working in a particular place, and we should like give back this information to farmers and technicians, right? But we're still not doing that, but we need to do a lot of research on that. Just to give you an example, in this new initiative, digital initiative of the CGIAR, we're working with Farm Radio International. But something that happened is like, okay, so we're working more at the system level. So we're trying to help Farm Radio International to make sense of thousands of voice messages that they have. But then the data scientists got stuck in, because they were kind of overwhelmed by the amount of information that we get even when they try to classify the problem. And it kind of reminds me something that we did in the big data platform, and we supported in an example of a project that we supported as part of a SPARA project called Farm Inc. So in that project, it was supposed to using Facebook in some countries in Africa to understand the dynamic of supply and demand of livestock. So that was the way how the project started. But then when the data scientists started to work to crunch the data and to classify and label the different information that they were getting from the models, we realized that it was not only the dynamic of supply and demand. We were also like understanding, or we're getting information on animal health, of outbreaks of diseases, right? Mm-hmm. So this is where we as CGIAR and as scientists, as universities, we can help data scientists like with expert guidance on the type of things, the type of results that we can also obtain when we're working with this type of databases, because then we talk with them and we say, look, eventually, if we can find a relation between animal health and climate, we can eventually work on an early warning system, and then how we connect that with the governments. So this is kind of our role, right? We help to connect governments to make, to support them on create these systems. We can do some research, obviously there, publish some papers. So that's the thing, like we're facing, like we're getting a lot of information, but sometimes the data scientists, if they don't have the expert guidance to interpret what we're getting, it's kind of a bottleneck. So this is, I think, where we have a huge opportunity to work together. And this is something that I've been talking with Jacob too, like how to make data-driven decisions based on such amount of information that we get in. We're moving from average, we're moving from having like information with a certain frequency to really get information day by day. And how can we use all those models to understand much better what is happening? How can we empower, for example, not only the decisions that are made at the level farm, but also the technicians. So that's why we were talking about also the extension agent of the future. How can they be equipped with this type of tools that can help us to make more decisions? I think that's all on my side. Thank you so much. And if you have questions.
I'll be talking about crowdsourcing and citizen science as one of the areas where we have developed work mainly on the production area, now also trying to look at whole food system area. And one of the things that we want to put these little slides here as a kind of a little challenge in the sense of this book that I just recommended to Danielle. So to also put it on a slide, there's this interesting book about how in a way statistics and certain ways of thinking about averages has limited development of systems, so to say. This book starts with a little story about the design of the cockpits and how a lot of accidents in the US Army with airplanes were caused by this idea that the cockpit should fit the average pilot. So they used data for 4,000 pilots to calculate averages. And so they made the cockpit exactly for the average pilot. And then there was a kind of a young graduate who came in to the army and had to work on these dimensions. And he kind of realized that actually only maybe 1% of all the pilots is average. If you look at all the dimensions of our bodies. So even if your average height, probably your arm length is not average, right? But that's important when you're in a cockpit. So in the end, nobody was average, right? And that's caused many of these accidents. And only when they became aware of this and started to design adjustable cockpits, they were able to prevent a lot of these accidents. There's kind of a conceptual change in thinking about averages and the extent to which we can actually use averages as a way to adapt to external circumstances. So how to be less addicted to the averages? Maybe that's one way to frame this call. So that means we need to, for example, to design for extremes rather than for average. There is no average farmer. There is no average farm. How can we design for a variety of farms? So that is where this stuff around user-centered design comes in, and the development of what we call personas, which are kind of typologies or for example, users that are extreme. So they're not average. You take somebody, so can we design for a poor illiterate woman who doesn't have a mobile phone? And what can you do with digital tools to still benefit this person? But also, how can we design at the same time also for somebody who does have a smartphone and is very well connected? Being more data-driven rather than hypothesis model-driven. So a lot of our statistics were developed based on what is called small sample statistics, Gossett, Fisher, etc. Basically based on data scarcity, right? And that's why they use normal distributions, etc., to work with stuff. Now, if we have much more data, doesn't that also not mean that we should not only rethink the way which we use these data and more machine learning, but also look at other assumptions that are kind of built into our system because of the use of these types of statistics. So we're thinking, for example, about genotype by environment interactions, which are looking at location and year effects. And we are still talking about that. Whereas actually have this complete wealth of environmental data that you could include into the analysis as covariates, for example. These kinds of things. So working also from focus on broad adaptation and technology that should work anywhere, but instead of looking at local experimentation trajectories where people discover things. If you work in, say, an agroecological approach, or even if you don't, but you work in conventional agriculture, still a lot of these things mean that you need to be thinking about local adaptation to be sustainable rather than fitting kind of the average situation, adapting things to your local context, to your local soil, rather than transforming the environment to be optimal for your technology that you bring in from the outside. It also means that it's a trajectory of discovery rather than something that you can predict. But maybe you learn about it by only iteratively actually implementing it and learning it while you do it, and accompanying these kinds of processes. And then maybe a bit less focus on efficiency per se, because we are making maybe the cockpit, so to say, very efficient for one parameter. But what about all the others, right? So maybe we should be more focusing on fit and having these more broader perspectives, maybe with less rigorous approaches, rather than this strong focus maybe on making on for example, raising productivity or resource use efficiency, but defined only in a certain way, right? But we only look at water and fertilizer because we don't have the data for all the other things. Maybe we should be more having cast the net a little bit wider and looking at things, even if we don't have very precise data. And how can digital technology help in all of this? First of all, being much more empirical, getting much more data is now cheaper, and also making better use of it to understand variability and extremes, not only in user types, but also in situations in time, for example. Having these much more direct feedback loops in these kind of learning trajectories. So in terms of the constant learning and what we call adaptive management. So rather than pretending that we can predict always what the future will be, rather being learning about it and anticipating and working with scenarios, for example, and working with these feedback loops is something that digital technology can also support. So rather than a strong focus on trying to use all this data to predict and control, looking at a more adaptive management paradigm where you adapt things. So for example, one of our collaborators, Joost van Eerwaarde, has just published an article that shows that it's very difficult actually to do variable fertilizer rates based on soil data in Africa. Probably you're much better off if you just take data on how much your system produces or your aspiration to determine fertilizer rates than thinking that you can predict how much fertilizer you need by knowing your soil very well. Soils are difficult, they're multidimensional. Then also just more intensive communication between stakeholders in systems about aspirations, about plans in the future. That's also where digital technology can help to build these feedback loops between extension, between research, farmers among themselves, different types of institutions that deliver services, including inputs, financial, etc. So I'm going to talk a little bit within this big context about citizen science, which is, I think is a very interesting approach to kind of tick many of these boxes in terms of thinking a little bit away from a focus on averages and involving your users directly into the research so that you can make these much more tailored recommendations. So there are different levels of citizen science. So the most basic one is crowdsourcing, where, for example, farmers or other users, or citizens collect data. For example, bird watching data. Most of the bird watching data right now is coming from crowdsourcing, people collecting these data. And if you want to write a paper in Nature about bird ecology, you're probably using most of these volunteered data, right? But then also going up different levels, interpretation, including interpretation, not just collecting of the data, but also what does it mean? And then even further going up, involving stakeholders in defining what the actual problem is. For example, in farmer experimental networks, many times the farmers define what the problems are they want to look at. And then at the highest level, where it's really fully collaborative, you have participation in all the stages of research, all the way from problem definition to analysis. So I'm going to talk about something where there has been a lot of participatory research already. I'm working with NGOs, it's Geretses, and also I start with the right point. I start with the farmer. So you see, I quickly arranged my slides. Now this is already there. So because this was for me was a very insightful moment. So this was in somewhere in West Africa, working on a project that I will not name, where I saw this situation happening in participatory variety selection, maybe now more than 10 years ago. So what you have here is a very capable farmer who has high levels of literacy. He was a schoolmaster of the village who had done an experiment and measured on every plot. They had measured 3 plants, and they'd written down all the data there. And in this workshop, what he was basically doing with this stick was to read out all the numbers one by one in a farmer workshop, right? And I realized something is not going very well here. One of the things is, like if you really look at it from a like hard-nosed statistical power perspective, etc., this was not good enough, right? For a scientist, it's not good enough. But then for the other farmers, like for the farmers in the room, it's also not very interesting to have somebody reading out all these numbers. So we have participatory science where scientists and farmers are supposed to collaborate, and it's useless for the scientists and it's useless for the farmers at the same time, right? So something is going wrong here. In some way, we're connecting 2 things in a way that is not generating any mutual benefit, but the opposite, right? It's useless. So what we tried to do when I started working in first in Bioversity and now in the Alliance was to say how this is a design problem, right? So you have kind of a paradox. Farmers actually like to do experiments themselves and learn a lot by that. But as soon as the scientist arrives on the scene, you get this situation where it becomes useless. Why is that? If farmers like to do it themselves, these experiments, why is it that we're not able to mobilize all this energy and work with farmers in a positive way? So by using a design approach that started with how farmers do their own experiments and then add a few things on it, rather than kind of trying to bring Sir Ronald Fisher to the field in Mali, so to say, can we get to a different approach? So can we collect data in ways that are feasible and robust, rather than hyper precise and scientific between commas? Because it's in the end you get this kind of pseudo precision, right? You're saying you're very precise, but what really happens in the field is something else. And this was inspired by citizen science. Before I was doing this, I had been inspired by, especially by data transcription applications where people actually transcribe data from logbooks of ships and did that on a voluntary basis to generate this huge climate database of Javier de la Torre in Madrid. And people signed up for it like enthusiastically because maybe their great-grandfather was the captain of that ship and it was his logbook, and now they're doing it. All these people interested in history of shipping and etc., maritime history, signing up to do all this transcription work with a kind of a social goal. It's amazing how these kinds of projects mobilize people to do things on a voluntary basis. And the other example, of course, is bird watching that I already mentioned. What has been successful in bird ecology is to really realize that these people are self-motivated, right? It's not us bringing carrots to them to come and do stuff like little incentives, like paying farmers little money or something like that. People do this because they like to do it. And as soon as you start paying for them, you're actually not recognizing their willingness and enthusiasm for this. You make it a commercial transaction. So that would be defeating the purpose. Then also they have invested strongly in good digital design, very attractive, very nice apps that do all sorts of stuff that also benefit them, like maintaining a list of all the birds you've watched with nice maps, etc., that you can then share with others and have alerts when there's a new bird somewhere, and so you can all rush to see that bird, stuff like this. Also, the other thing in citizen science is to chop everything up in very doable little tasks. So that is maybe a little bit less evident here, but every citizen scientist only collects a little bit of data, and it becomes something interesting for a scientist when you add it up. And then also the other thing is that you then adjust the statistics. So you don't impose your statistics, say we need to do an ANOVA, we need to do a randomized design here, so I'll teach the farmer how to do it, or I'll do it myself. But you think the other way around. How can my statistics do something with data that I can get in a feasible and a robust way from this process where I generate information? So what we designed, and I don't have a lot of time to explain it, but it's kind of a scheme that goes from basically the computer to the computer. So it's not farmer to farmer again, it's computer to computer, but the farmer is clearly in the middle and all the rest is being adapted to it. So what the farmer can do, we discovered in a couple of iterations, farmers can do very well is test 3 varieties and tell us which is the best and which is the worst out of those 3, like a ranking for many traits, including things like yield, but also certain types of diseases, etc. That is very feasible, doable. An individual farmer can do it. So it's a micro task. It's not, you don't rely on organizing farmers in very complex ways to come together to one big field and doing all sorts of complex designs. And then all of the rest you can adapt to it. So it does exist, right? This is called an incomplete block design. It does exist if you look at the literature. The statistics that we then use to do the ranking, and as also they existed, it's just that nobody's really had properly implemented in software. We discovered that all of the elements to set up a system like this existed in the literature and were done somewhere in one condition or another, maybe in combination with other things, not like a system, not thinking about it in this way. There's nothing new about it. What's new about it is the combination of different approaches. So we call this a triadic comparison of technology approach, TriCOT, because it's three plots. So it starts with the design of the experiment even on your computer. So you can also, two sorts of organizations can do this in a very robust way, because then you standardize things, and when the data gets in here, you already know the structure of the data, you've defined all your variables and so forth. So the technology takes care of the back end and makes it very robust to then implement this. It does the randomization for you, kind of a balanced incomplete block design. Then you, within the QR code, you link every package to a farmer, so it's very robust. No mixing up of the samples. You collect the feedback mainly in the form of ranking. You can also do a few measurements if you have the resources. So we're looking, for example, now at very robust yield measurement protocols with farmers, which usually is much more robust when you do it with volumes rather than weights. And then all of it comes together and you get your statistics. So we've also then looked at, so how can you then adapt your statistics to this? So we've been implementing this, the Blackett-Loos model, which is also an existing model. It's written, published in the 60s, 70s. It's never implemented in software, not in a proper way. Maybe somebody with Bayesian statistic for some very peculiar application. So we went back and actually commissioned this to a group of very good statisticians who then implemented it. You can do fantastic stuff with rankings, by the way. It's fascinating what you can do with rankings in terms of statistics. But I don't have time to explain that. But then if you have, so you have data from a lot of fields, if you implement this. So this is one trial where we had 5 seasons of beans. Beans is a nice crop because you have 3 cycles of beans here in Nicaragua. And then with, because we have GPS points, we have planting dates as well, you can then link it to climate data and do all sorts of interesting statistical things. So one of the things that we discovered is that by just taking the data and analyzing it, we got kind of a textbook result back in a sense that at 19 degrees, maximum night temperature, you saw a difference in variety performance. So the heat tolerant varieties started to outperform the non-heat tolerant ones when you get warmer nights, right? That's, if you look at the textbook, it's 19-20 degrees, and maximum night temperature comes out. It's pretty recent that people have discovered it's actually maximum night temperature that influences the heat tolerance in beans. But these are purely farmer-produced data and public data from climate that gave us this result. And you can then start to map out which is the best variety for which area, looking back also with more climate data, not just for the trials, but long-term data, etc. You can do all sorts of very interesting things with these data based on data that's really close to the farmer, right? It's farmer to farmer. Farmer generates data, do all this complicated stuff, but in the end you get back to this is the best variety for your area. If you want to deal with heat tolerance, which actually we discovered in many of these places, which are cool relatively, the local varieties are as good as the new ones because the breeding has mainly focused on heat tolerance. So the difference was not so visible. So this is very focused on production, and now our challenge is also, like if you look at the whole food system, production is one part of it. A lot of the other challenges are in, say, going all the way to diets, but in this kind of in-between part, like the going from production to trade, and then diets. So we're working mainly with colleagues at IATA who've done crowdsourcing work focused on diets in Rwanda. This is also a little Inspire project of the big data platform. So you see it coming back, these little investments as well, and we're making good use of them. So this usually nutrition scientists, what they have is very precise data, supposedly, of a few households in terms of nutrition, where they go once, and they do a lot of enumeration of everything that you ate the last 24 hours. It looks very precise, but it's only a 24-hour snapshot. You have to repeat that many times to actually get proper data. This takes a different approach.
Sorry, and they'll visit once per year.
Once per year, maybe. If you really do it very well, you do it 4 times. So you have 4 times 24-hour recall. And then we know people are not good in terms of memory of what did you eat last night? Exactly how many grams? It's difficult. This is a different approach. This just asks you what food groups did you have, and then does it very many times, so you can get a much better understanding of time trends, for example. So it takes it's complementary. It's not saying that the nutrition focus is wrong, etc. And a lot of that has been very well calibrated, etc. But having this kind of almost real-time view of what is going on is very useful, complementary time of data. So you get these kind of real-time trends. You can start to look what was the influence of COVID. I won't explain that. I don't know how good it is, but this is preliminary results, just to have some slides of kind of an impression of what you can see. So you can see what kind of data outputs. You can see by food group, what is the frequency of presence. You can see kind of correlations between intake of different food groups, and you can start to look at these data. But this is very preliminary work. But what we did get out of it is that it is feasible to get these kind of data, and they don't look too bad. So we're really thinking about, like, okay, that's at the end, but what is missing is this kind of stuff in the middle. So we do something about production, we do something about consumption and diets. What about this big, huge bit in the middle of food systems that are not visible at all? Food trade. And for example, this is a very recent publication that looks at food flows in the United States by looking at subnational data. Actually, this is not really data on the food flows. This is just modeling. It's looking at your surplus or your lack of certain food items in these different subnational levels, and then just drawing a line to the shortest place to kind of link a surplus with a shortage. And you get this nice map. Maybe the reality is completely different. If you look at economic literature, economists always look at prices. Very few times they look at actual physical flows of food from place A to B, like taking a really geographical approach. People have been doing this in the 1970s, especially with really fascinating results, especially geographers and anthropologists. And then it kind of died out. Nobody's doing this kind of stuff. What we want to do is kind of revive this area. So we think it's super relevant. Like if you then look at stuff like infrastructure decision making, World Bank defines a project to build a road between two places and invests a large amount of money. We could start to say things like you should build this road here because that would connect these two areas that are complementary in terms of agricultural production. And the actual food flows, now they go like this, but then you can go like this. This is focused on Rwanda. It's a quite interesting article, again, like 1980s, before the genocide, that actually shows that, that Rwanda was very disconnected in terms of food systems. And that was why food prices are really high in some areas because of the lack of trade, not so much the lack of production, the lack of trade. Now, we want to really get a much better understanding of these kinds of things. And then also other types of investments. And you can then start to compare it, right? Should I be investing in this or this other thing? Maybe it's not a good example. We don't want people stop investing in breeding, but it could be other types of things. You can really put quantify the benefit of different investments in this area. Okay, those are some examples. You can look at trends of network resilience also in time. What if this happens in terms of scenarios? Do you have the ability to transport different food items from A to B? Food trade is really coming up also in East Africa. Self-sufficiency is difficult when you have urbanization, etc. So we need to be looking at this. Urbanization is really strong in also in Africa. Some of the biggest cities in the coming decades will be in Africa and in Asia, of course. That is one of the areas that we would like to also talk to you about this other bit of the food system. Thank you very much.
So good morning, everybody. My name is Léa Courteille, and I have a background in environmental science and computer science, and I'm going to present to you my PhD topic, which is towards an interactive and participatory mapping of soil multifunctionality. I'm still in my first year. I started in November. And as you will see, my topic is pretty interdisciplinary. So I'm supervised by many people. Philippe Lagacherie for soil science, Léa Tardieu for environmental economics, and Nadia Boukhelifa and Evelyn Luton for computer science. So as you may already know, soils have many properties. For example, pH, stone content, depth, clay content, sand content, and so on. And these properties condition the ability of soils to fulfill some functions. So you may think first about agricultural production, but there are other important functions like storing carbon or regulating the water cycle. And these functions are at the basis of some ecosystem services that soils help provide to human societies. And so as a consequence, if soils are degraded, the number of functions that are fulfilled decreases, and it may, the number of ecosystem services that are provided also decreases, and soils cannot play their part of supporting human societies anymore. So it's very important to protect our soil. There are many different drivers of soil degradation, like climate change, deforestation, urban expansion, and many consequences of this, like reduction of ecosystem services, like I said, but also migrations, more rapid climate change. And so, it's very important to protect them, and the Food and Agriculture Organization comes up with good practices and ways to go. So my thesis is about protecting soils, but protecting them in a specific context. So the type of soil degradation I'm dealing with is artificialization, which can result in sealing. So the definition of artificialization is still controversial, but it's basically when you take an agricultural surface or a forest surface, and you convert it to a park, a golf course, or if you put concrete on it. If you put concrete on it, it's called sealing. But yeah, basically artificialization just prevents the soil to fulfill all the functions that it's supposed to fill. Yeah, and this artificialization is driven mainly by urban expansion, and it results in a reduction of ecosystem services. So the main assumption behind my thesis is that we need to avoid, of course, artificializing too many soils, but it can happen that we have to artificialize. So for example, we have to build new houses. And so if we really have to do this, we want to make sure that we don't put concrete on the most multifunctional soils of the region, like the soils that fulfill the most functions, because we might endanger the sustainability of our societies in the long term. So yeah, the question behind my thesis is, where are the soils that should be protected against artificialization by urban extension in the Occitanie region? So the Occitanie is the region Montpellier is part of. And yeah, and so as I will explain, in my thesis, I will implement many of the practices that are listed here. So I will develop a soil information system, that will assess soil condition, like soil multifunctionality, in order to raise awareness and promote more inclusive soil governance. So yeah, for decision makers not to decide to artificialize the most multifunctional soils of the region, they need, of course, to be aware of the soil multifunctionality in the region. So it's useful to give them maps of soil multifunctionality. These maps can be obtained. So first you have to map the soil properties. This is done by what's called digital soil mapping. So basically we take data we already have maps for example, climate data, satellite images, geological data, which kind of represent the soil forming factors. So factors that influence soils. And through machine learning, we learn to predict soil properties from these covariates. And yeah, and then, as I said, like, well, functions are linked to properties, so we can easily obtain maps of function fulfillments, and then we can combine them. So here it's a weighted average. So the higher the weight, the more important the function is in the multifunctionality index. And then we have a static map of soil multifunctionality. And these maps can be used for decision making at different scales for different purposes. So yeah, these maps were obtained in the frame of a project called Artisol, which ended just before my thesis started, and my thesis kind of builds on this project. And this project enabled us to get feedback from stakeholders, and it enabled us to identify the limits of such static maps. And yeah, we saw that these maps face serious acceptability issues. And yeah, so the limits are that first, digital soil mapping models, so the models here to predict the multifunctionality maps, are not very accurate, and they need to be made more interpretable. So it's kind of a machine learning issue here. Then yes, sorry, I forgot to say that from the machine learning step on, you get a pretty significant uncertainty value because soils are very hard to predict, so the uncertainty values can be high, and this needs to be propagated along the pipeline and communicated here. And the Artisol project showed that the uncertainty values are often poorly communicated, and therefore they are ignored by the users because they cannot really interpret them. So this leads to biased decisions. And so this is kind of a data visualization issue. Then maps are not adapted to local contexts. So for example, if you need to take decisions about soil in an area where the flood risk is high, you might want to give priority to the flood regulation soil function here, and therefore give a higher weight to the function in the formula of the index. And yeah, in general, stakeholders don't take part in the mapping process. They feel kind of excluded and their expertise is not used. So sometimes they even see mistakes on the map because, like I said, the models are bad, so and they cannot correct it. So they feel like the maps are not worthy of consideration. Yeah, so the goal of my thesis is to build a software, like a digital tool, in consultation with the end users. So it will be a co-construction. And the goal of the tool is to provide interactive, as opposition to static maps, to users, so that the users can like adapt them to local contexts, correct them if they see mistakes, etc. So during my first year, I envisioned the interaction levels I want to implement. It goes from the most superficial to the deepest. The deepest level is modifying the soil properties, the maps of soil properties. And you can see that the deeper the interaction level, the more expertise you need to have. So briefly, I don't have much time to explain, but you can see here that it's very small, but as the spatial resolution of the map, the coarser the spatial resolution of the map, the lower the uncertainty levels are. So there is a compromise between spatial resolution and uncertainty. And the first level would be to let the users choose the best spatial resolution so that they can still make decisions at the scale they need to make a decision, and while having manageable uncertainty levels. So it will be kind of an interactive visualization functionality. The second level will be about letting users modify weights in the formula so that they can give information about the most important functions at the local level. And then through an optimization algorithm, we will obtain like a consensus between all the weights that were entered by all users. And the third and fourth level are about modifying maps of soil functions and soil properties. So this is addressed like this will we will I don't have the word, but this will be for farmers or like soil scientists that have a good expertise. Yeah. So yeah, I don't have any results to present. I'm still in my first year. So the takeaway will be that I am combining methods from 3 fields to develop a digital tool that will help make better decisions about soils. Thank you for your attention.
Thank you for having the floor. My name is Yulin. I'm currently a candidate for PhD diploma in the Mixed Research Unity ETAP on this campus. And I'm also on in the end of my first year right now. So the topic that I'm going to present today is to use crowdsourcing agronomic data to inverse a soil water balance model for grapevines. And hopefully this project will help vine growers to benefiting from data collected by themselves by providing them useful information to adjust their farming practice in the context of climate change. So before I begin, I want to precise 2 terms in this title. The first one is crowdsourcing data. I believe many of you have already known this before, but the crowdsourcing data for us is are data which are not generated by researchers, but by a group of people driven by motivations to extract certain benefits from their perspectives. In our case, such data is a growth index for grapevines. It is useful for vine growers because it tells them how thirsty their grapevines are at a specific date. And thanks to another PhD thesis also financed by DigitAg, a mobile application called ABEXVIN was developed 4 years ago, which allows calculate very easily the growth index by classifying the shoots of vines into 3 classes using a mobile application. And that's how our data are crowdsourced. And the second term I'd like to precise in this title is inverse modeling, which allows us to invert soil water balance model. There is at first modeling, then there is inverse modeling. The modeling is a common scientific practice which simulates a system. And for example, we work with a soil water balance model, which basically describes the exchanges of soil water with plants and the atmosphere. But in order to make this simulation, some pre-required knowledge have to be obtained on the soil property, which is not necessarily the case. And here comes the utilities of inverse modeling, which consists of using observations of what a model models to estimate what some features about the model itself. Like we can estimate some soil hydraulic properties using soil moisture data. And the growth index that I presented just now is particularly interesting because it is very easy to obtain, unlike soil moisture data, which commonly demands different sensor to plant it in different depths of the soil. It is very easy to obtain this growth index because we can imagine a vine with its roots like a sensor that we plant in soil, which responds to soil water dynamics by adjusting this vegetative growth. When a soil is dry, a vine grows slower, and vice versa. So what we can imagine is to use the growth index observation as an observation for inverse modeling in order to estimate a very important soil parameter for viticulture, which is the total transpirable soil water, which actually means the maximum amount of water grapevines can extract from a soil. Okay. This parameter is very important for viticulture, but it's very time-consuming to obtain in field conditions. Yet the stake related to this parameter is climbing up because of our climate, where both droughts and floods seem occurring more frequently in our region. And knowing this parameter actually helps vine growers to have a more precise idea on the resilience of their vineyards towards extreme hydraulic conditions caused by our climate. Ergo, the first research question or research direction, we want to use the growth index to make inverse modeling in order to estimate the total transpirable soil water. And I remind you that our data are crowdsourced. So thanks to the ABEXVIN, the application, since 2019, there are already more than 20,000 observations of growth index made by agriculture stakeholders in our region. So naturally, after finding a way of making the such inversion at a rather local scale, the next step will be to upscale this process. Precious information is expected to be drawn, like the spatial variability of the estimated parameter, which hopefully will contribute in regional water resource management strategy. However, in order to do that, there's a problem, which is that the growth index is not a typical variable that we use in inverse modeling to estimate the total transpirable soil water. So what we are now attempting is to use a link variable, which plays a role like a bridge which connects two sides. So in the middle, we have the link variable, and on one side, we have what we observe, the growth index, and on the other hand, we have what makes inverse modeling possible, which is another agronomic variable. But we have found out is that this bridge, the model that models this bridge is very uncertain. What we have been trying is to implement a probabilistic framework, like shown in this figure on the left of this slide. Given each value of the growth index, not only one value of the link variable is predicted, but a distribution of it. What is interesting is that certain values of the link variable that interests us is more probable than others. Okay, okay, this is still a work in progress, but the idea is still to continue in the probabilistic framework in order to identify and quantify different sources of uncertainties, because our uncertainties are the uncertainty is actually a hot word for us because we work with crowdsourced data. Basically, we don't control the process of data collection. Data can be imprecise, data can be totally missing during periods which interests us. And that underlines that specific statistical tools have to be adopted. And what we have found out today is that such type of data cannot be treated in an isolated way. Okay, on the one hand, that means instead of considering only one single observation of growth index, we can consider its dynamic. We can consider what happens before, and by using a simple mathematical model, we can model a continuous dynamic, which allows to alleviate the fluctuation in the data, and also making predictions for periods where no actual observations were present. And on the other hand, instead of considering merely one dynamic, we can also use a probabilistic framework using the Bayesian approach by introducing prior knowledge on how this dynamic should behave. Like shown in this figure, even with only some observations of the growth index, we can still have a global idea on how dynamics should behave in the future. And by collecting more and more data, our estimations become more and more certain and constrained. And what is interesting here is that we use not only data collected by professions, we can also include them in some sort of data analysis, which corresponds some part of the presentation given by Mr. Jacob. And to summarize, I would like to say that the use of crowdsourcing data in inverse modeling is a new but developing practice. We can see potential in it, but it's also challenging. And adequate methodologies, statistical tools have to be adopted to account for uncertainties in those data. And these are two take-home messages I would like to share with you. Thank you.
So good morning. I will just present the ontology development work we are doing in CGIAR, led by, in fact, the Alliance. It's probably the less technical in terms of cutting-edge technology, but still, I think it's a very good groundwork. I just want to mention, referring to the big data platform, as you mentioned, we are still having an ontology community of practice. It's hosted by the Digital Transformation Initiative, where Daniel and Anna are leading work packages. So we are still there. And this community, in fact, is composed by a large amount of members from any expertise, in fact, because you can subscribe freely to the LinkedIn group or to the newsletter, or you can also subscribe to our YouTube channel where we have recorded seminars. So it's a large range of expertise from ontologists to data scientists and machine learning experts. So one of the challenge of a pipeline of digital tools, like Jacob mentioned this morning, it's how do you define or how do you describe the information item that is carried out along this pipeline of tools, from data collect to storage to analysis, and finally create useful information for farmers. So the ontology, as you know, I suppose you know the FAIR principles: findable, accessible, interoperable, and reusable data. So for interoperability, the meaning of your information item is very important. So you have to describe it using this terminology that we call, this terrible word called ontology, but that helps describing. Oh, sorry, I have a recorded slide, sorry. So I don't was surprised. I myself. So I just wanted to say that we have several working groups. I'm just working on specific domains for developing ontology or reusing what exists. So we have one on the phenotyping of plants, one on agronomy, so all the field practices, one on socioeconomic data, another one on aquatic food. And the last group created was to discuss the data standard ontologies for UAV data. But I will focus only on crop ontology and agronomy because of the time given to me. And the crop ontology is one of the eldest tools we have developed. And the first objective of that ontology was really to help with providing a standard nomenclature for the values recorded in the field on crops. So clarifying what is a trait and what is a variable, because when we started this work more than 10 years ago, thanks to a Gates Foundation program, it was unclear. And there was a lot of messy data coming from the breeding programs. So we defined what was a trait. So it's an entity and a quality. It's what you observe and the quality you want to measure. And the variable is described in our guidelines very well. It's the combination of the trait, the method used to observe or predict or measure, and the scale of the unit when there are some. So this model has been, in fact, adopted by many breeding databases, but of course nowadays we are getting more ways, more data streams, different data streams with modeling, with machine learning. So we have been revising our guidelines to add to our method classification system, the prediction and the classification. This has been done, of course, at the request of the scientists. So you can go to our guidelines. The cropontology.org is the website where we publish all the trait dictionaries per crop, because our first objective was to help breeders. So it's a crop entry system. And so per crop, you have an ontology. And you can access 33 crops, one algae that was submitted by Cornell University, it's sugarcane, and you have more than 5,000 traits and more than 7,000 variables available that can be reused, that describes, provide a definition to a trait. It's fully compliant and reused by the breeding API and the MyAPI standard for phenotyping field clients. And it's indexed by two major well-known portal indexing ontologies, Agro portal developed by Inrae, and Jiménez, ontology research lookup service of ABI. So of course, having crop-based ontologies create kind of, I would say, segmented semantic environment, because you focus on banana or tomato or pod. So we got an NSF funding to collaborate with Oregon State University and manage to map our crop-specific traits to more global specific, more neutral traits in the reference trait ontology. It's called the mapping of ontologies. And it was the work of Marie-Angélique in the NSF project. The idea being that if you search for fruit color, the search system should help you finding finger color, berry color, and pod color, and bring back the data. So it was done in the perspective of, for example, genomic comparison, but it also helps to bring data per family. So this has been a very nice work. So working on the agronomic trait is now not sufficient. For breeders, we need to bring other traits from other market segments. So we have been working in the framework of RTB Foods with CIAT, and particularly I've been working with Amos on extracting from food scientist lexicon that are developed for sensory panels, concept about the qualities of the food product derived from the varieties. So as it was done for RTB, it's fruit, tubers, and banana, you have the list of food products that have been tested and for which we have already extracted the concept with the scale and the definition and how to evaluate. So we have been working with food scientists on that. We also have been led to work with social scientists about how to extract the variety trait preferences collected through surveys to focus group or to consumers, traders, and processors. And we have been facing some difficulties because, of course, a preference is usually given by the farmer in his own representation of the qualities. And then the social scientists surveying have tried to add what they call indicators that would give the context of, for example, what means a cassava, a bulk cassava that has a good smell. So we have been working at developing solid indicators out of the preferences that we could capture in our ontology, and also try to break down some of the preferences into measurable breeders' traits, like what means a big bunch. It's a combination of weight, finger circumference, length, and number of clusters. So this work has been done in the context of RTV food. We also are working on trying to define what are the market segments that are used for defining a breeding product. And this is quite complex because a market segment is very contextual. So how do you describe the farmer, the consumer, the trader, the processor in a given region? So we have been discussing with social scientists to extract key elements that would help characterizing the market segments breeders would like to target with their product. And then we have recently made a survey. It was in September. We got the first results about who is using the crop ontology and for what. And we had an answer, and mainly responder were scientists, some data managers, and few database developers. So we see that the scientists are using our ontology as a resource of terms, and they like to submit terms because after they can refer to the term and its identifier in their peer-reviewed papers. And you see that 31% of the users are from Sub-Saharan Africa, followed by Europe and Central Asia. The key users of our tool are listed here. So you see it's a combination of public and industry partners. So either they are contributing or they are using our resource, which is fully contributed. And soon, two new tools we are collaborating with are CliMob and Artemis, and we will soon list them in the user of our ontology. So the second product I wanted to focus on is the agronomy ontology. It was led by Marie-Angélique, she's sitting there, with the help of Céline, and it was done in the context of the agronomy trials. Now, so it's embedded into the Excellence in Agronomy initiative with Meda de Varé. So the agronomy ontology describes all what can happen in a field, either a management by fertilizer application, a process that is planned, or unplanned processes. And it's really describing very thoroughly all the steps taken for managing a field. So this is the structure of Agro. In fact, the main principle taken for developing the model was the trial, the agronomic trial, where you plant a crop and then you can apply a fertilizer, which is a process, of course. So the experimental plot is kind of the unit of that ontology, around which you have all the elements like seeding process, planting implement, etc. So you can describe everything happening on that trial. However, now more and more users approach us to make from that ontology something more holistic, so you can also have on-farm practices and not just agronomic trials. So this is the model developed mainly by Marie-Angélique. She can give you details on that model, but the most important thing to know is that an agronomy field information management system led by Meda de Varé, called AgroFIMS, is really embedding that ontology to describe all the variables an agronomist can measure. So it helps the agronomist to define the field book, selecting the terms, and then the field book is ready for the data collect. So we have some new projects coming. wants to go wrong. Okay, so CleanMob. So Jacob mentioned the project, of course. So the project is led by Jacob, but we work closely with Carlos Quiros, who is the co-leader of the digital solution, to make sure that at least CleanMob can use the crop ontology and the economy ontology as a resource for describing the threats that scientists would like the farmer to assess with the 3 varieties. And then it also leads us to modify a little bit our tools to encompass all the way farmers are describing their crops and of course the method used for assessing those preferences, the TriCot method. We also are working with David on Artemis. So David is leading that project. Jacob mentioned it. It's about having sensory devices measuring several threats on crops that are relevant for breeders in a new way using machine learning behind for common bean, cowpea, and sorghum. And of course, the idea being that for at least all the images taken through a phone app can be tagged properly to have the machine learning algorithm to extract the threats at the first steps. Of course, it can be after certainly doing that on its own. So the annotation would use the crop ontology threats that already capture a lot of breeders' threats and the agronomy ontology as well. And we are also looking at making the project data fair. And the last new project we are engaged in is the periodic table of food initiative. So it leads us to look beyond the production, of course, segment. And here, the idea being to have a public database with quantitative and qualitative analysis results on most important foods. So we have been asked to work on tagging all the food sample or the food product with the food ontology, which is the farm to fork ontology, and help with the aggregation of data coming from different analytical labs. So this is a very new project. Oh, there is the name of Jacob. He's the leader of the...
Good morning, everyone. I'm glad to present my research project entitled Ontological Formalization of Mathematical Equation for Phenomic Data Exploitation. I am in the 3rd year of my PhD, Felipe Vargas. Oh, it's not studies in food science use data that is multi-source, multi-scale, and is really complex in nature. So to manage this complexity, the scientific community is using semantic web approach. What offers the semantic web is a set of technologies that allow to manage this complexity of data with flexible technologies like data models to represent these multi-schema data set. So on top of these technologies, the scientific community is developing information system. One example here in Inrae is the plant phenomics information system. But how the people use the data from this information system? They extract the data by consuming web services. And these web services offer the data in a tabular format. So then they use this tabular data to perform some data analysis. And within this data analysis, they perform some mathematical equation. So examples from plant phenomics are like the vapor pressure deficit, the thermal time, and some conversion of units of energy information. So for example, the VPD is a mathematical equation that uses the temperature and the relative humidity. So in an ideal scenario, in a first iteration, the scientific can plot the data and have everything okay. But what happened in a realistic scenario is that in a first iteration, they have the data incoherent. So they have data that they need to analyze more, and to perform some very time-consuming pipeline, they need to analyze, for example, what kind of ontologies have been used. They need to analyze to filter the data, to perform unit conversion, to check for outliers. to perform some equation finally. So the general question is how the semantic web technologies can help to reduce this time-consuming pipeline. So to address this problem, we define two main objectives. The first one is about the representation of the mathematical equation using semantic web approach. But these equations are no normal equation. This equation has to consider that the data is heterogeneous. So for example, the temperature can be in Celsius, Kelvin, or Fahrenheit, as well as it can have multiple granularity. So the information can be daily, weekly, or monthly record. So the first question is about how to represent this kind of mathematical equation in the semantic way. So then, if we are able to represent this kind of calculation, if we are able to have 100 or many mathematical equations in our system, it's really difficult to materialize this. So we need a smarter approach in order to compute this data. So the second objective is about a query answering method in order to perform the equation only when the user asks for them. So having a query language that is asking for a specific equation. So we can have, in addition to the VPD, we can have the thermal time or different conversion. So we need to analyze the query in order to compute only on demand what the user is asking for. So this is the second objective. So our field result is a proposal of a language to represent the mathematical equation. In the right side, we have the human readable mathematical computation, but in the left side, we have a machine readable computation. One advantage of this proposal is that we are using semantic web approach to represent the equation in a declarative fashion, independent of a specific programming languages. And then we are also proposing we are also contribute to the pair principles, and we are as well close to the mathematical notation. And to propose this, we base our work in several semantic web resources, like the technology of Charcoal that allows to describe constraints in the semantic web to validate and to improve the quality of the data. But it can be extended in order to define, for example, mathematical expression or rules. So this is based on that kind of technology. So the second result is about how to extend this mathematical expression in order to allow to manage quantities, because the numerical data gathered from the sensor are more than simple literal numbers. So they can be quantities that has a unit of measurement and a specific value and more metadata. So in order to do that, we define some functions that allow to harmonize the data. So given a context of heterogeneous, for example, temperature records, we are defining expression that allow to say, I want to perform this computation, but I need all the data in a target unit, like, for example, Fahrenheit. So for define this equation, we don't code a specific programming function, but we use a standard like QDT, because QDT offer metadata to do unit conversion automatically. We use as well Charcoal and Sparkle to do the computation on the fly, to perform the computation. So these are very non-invasive development, and is evolving, because if QDT add new units and new metadata, so automatically it will be part of our proposal. So finally, we propose an algorithm to perform equation on demand. So this is an ongoing research. We are still analyzing the algorithm, but basically we start with a query. If we asking for example, the VPD directly to the data, is going to return our empty result because the VPD is not yet materialized. So we need to analyze what the query is asking for. So the first task that we developed is to rewrite the query in order to remove all the calculable data, and it allowed us to retrieve only the observation concerning, for example, the specific experiment. And with this data set, we are going to perform the equation necessary to avoid to do many computations. So basically, we have here a proposal to represent mathematical computation. We based our approach in three main modules, like representing the mathematical expression, conforming fair principles. Then we have a module about exploiting metadata and for example, Unix ontology, but also we can exploit, for example, information from domain-specific units. And finally, we propose to compute all of these using semantic web engines like Shackle and Sparkle. So this approach demonstrates that the semantic web can be actionable for enriching scientific data. Thank you.
Hey, good morning, everyone. I hope you still have some energy to hear about data-driven sustainability. So just a little recap, just about where we are. Basically, that's what Jakob presented this morning, and I'm going to present the work of this data-driven sustainability team led by Tiffany Talsma and myself. What we are trying to do is translate our research into impact, and to do so, we work with a lot of different actors. We work with big agri-food multinationals, but we also work with governments. We work with even NGOs that were mentioned before, or investors in sustainability, and we try to tailor tools to their needs. So we will not develop the same tools if we're working with a big multinational or if we are working with our local NGOs and so on. And all those tools, the goal of those tools is try to get landscapes or to get areas into a more sustainable management. So basically, how do we work to try to get to there? We have first our strategy and donor engagement team with myself and Tiffany. And then we have 5 kind of pillars of research into social design, ecosystem services, land use monitoring, data science, and climate. And we are trying to bring all of this together into 3 kind of steps. In the development, we've got first the research and development, where we are piloting ideas, like creating new tools, but in the labs, where we are kind of developing new ideas. Then we bring this into real projects that are developed and implemented on the ground with real actors, with multinational or with local communities and so on, but that are actually projects that are implemented on the ground. And once we tested those tools into real project, we try to develop those services that streamlined at a relatively low cost, those tools to bring them at scale to other actors, or to, like if we worked with one multinational, maybe we will try to then get multi actors to use those tools. We are still developing this area, so it's not ready yet, but it's basically what we are trying to do, the streamline that we are trying to develop. And to give some example of what we are doing, first I will present this work to zero deforestation commodity chain and some risk analysis at landscape level. And basically here, the users are either cocoa or coffee traders. So they're buying the raw materials in the countries that are that are growing those crops and selling them to big companies like Nestle and so on. Many of those companies, including Nestle or Barry-Callebaut, Mondelez, and so on, have made a pledge to reach zero deforestation commodity chain. But in reality, they don't know where deforestation is happening in the commodity chain. They have, it's very difficult to them to know that, for example, if they're buying a certain amount of cocoa in this district or this commune, is it at high risk of coming from a deforested area or and so on. So they have no idea of what's going on in terms of deforestation on the ground because they are very removed from the farmers who are actually growing the crops and from the context. So we are going to provide them with commodity-specific information to aim to support the planning, assessing what are the risks of buying a certain commodity from a certain area. And to do so, we will kind of create a data stream to them and tailor to them, showing different metrics about different landscape. To do so, we need to map certain commodities like tree crops, and those tree crops are quite difficult to map because basically a tree is a tree, and seen from remote sensing with very rough resolution, say at 10 meters resolution, you will not recognize a tree only based on the spectrum information. But if we look at the structure of those trees in the landscape, we can see that a palm plantation, and here is a cocoa system with some shade trees and so on, looks quite different in the landscape, the structure in the landscape. So what we are trying to do is to use this spatial distribution of the different colors and different trees to map different tree crops and different commodities, and to be as commodity specific as possible. So we will try to map, for example, coffee, cocoa, etc., and then say, okay, and it's cocoa with adequate proteins, or it's cocoa with full sun, so no shade trees at all, etc., So we're trying to describe landscape as precisely as possible. To do so, we use those very well-known convolutional neural networks that are now everywhere in the literature in deep learning. We use Sentinel-2A, 2B data, and Sentinel-1A and 1B data. We extract a lot of features from those imagery. So basically, we take 1 year of imagery. We extract about 65 features per bands and per. So we've got a lot of data at the end of the day, and then we run those deep neural network on the data. I won't enter into the details, but if you want to talk about the specific details and how we do the pooling and so on. Then we've got a lot of data that comes from the ground. It can look a little bit messy, but it's how it looks, and it's always a nightmare to work with so much data. So we've got about 35,000 data points that comes from different sources. So some data points come from the private sector directly. Some data points come from polygons that were collected by scientists on the ground. We've got polygons that were mapped manually on high resolution imagery and so on. So we've got all this data that comes at once. Then we have a big work of curating those data. And at the end of the day, we're able to create high resolution maps at pretty large scale of different commodities. And here we see we are mapping coffee, orchard, rubbers, forest, etc., trying to be as specific as possible in the type of trees that we are mapping. In this case, it was particularly tailored to aim at coffee. So our commodity of interest was coffee. So that means we will try to be as precise as possible with the coffee, and maybe we will be less precise with other commodities or other types of land cover that are less of interest for the industry. But the type of result we will obtain, so like for coffee, we will have at the end of the day a user accuracy of 91 plus minus 8% of accuracy and so on. So it's pretty high accuracy, and something that I was saying before is the commodities of interest. So we're talking about deforestation, we're talking about coffee. So of course we need a lot of accuracy in the forest and coffee mapping. But then if we look at orchards, our accuracy is pretty low. It's because the user that we were targeting in the private sector that we were working with was interested only in their commodities. And that might be, and that can be, a limitation of this type of approach where you're working with only one actor, is that your product with, at the end of the day, will be very precise for one certain use and less for others. But in this particular case, we were working with the private sector interested in coffee. And another problem with this type of maps is then we will show basically many metrics showing you have in your commodity chain these areas where we see that coffee is specifically driving deforestation, and this area is then at high risk of having coffee coming from deforested areas. But there's still many people living in those areas and growing coffee or growing the commodity of interest without deforesting. But what will happen with the private sectors, and the first thing they will do is say, okay, so those areas are high risk. I will just stop to go there. I will stop to buy any product coming from this area because it's flagged as high risk, and all the communities that are living in those areas will suddenly lose a big part of their income just because it showed as high risk on our map. So that's something we want to try to to avoid. It's not the best. So we are working also with the private sector, in this case in Ghana, to try to find solutions to this problem and how they can still operate in areas high risk of deforestation, but still buy the commodity and still trying to reduce the risk of having deforestation driven, in this case, cocoa. So that's just a pilot that we are doing in Ghana, where basically we're working with a big multinational, Montpellier, who's buying a lot of cocoa in this area and want to have an intensification intervention in many of their farms in this area. The problem is that the way they would operate normally is to take this big protected area and say, okay, I take a 5-kilometer buffer or even more kilometer buffer, and I will not do any intensification in this area close by to the forest because I want to reduce the risk of deforestation from our activity. So what we propose is, instead of doing so, go do your intensification in this area, but use a margin or a fraction of the benefit you will do in this area to create a PES, or a payment for ecosystem services, in the protected area together with the local communities. So the local communities that are nearby the forest will maintain their, or will even increase maybe a little bit of their income by protecting the forest, while the rest of the area will increase their incomes through the intensification. We are trying to build this type of models, and to do so, again, we will use remote sensing and machine learning to first find the best area for the intervention, the conservation work, like find threats, like where's mining going on, where is cocoa really a driver of deforestation? Because if your commodity is not a driver of deforestation, you have no leverage in the landscape, and so on. But in this case, what I will show is how we use remote sensing and machine learning to kind of assess what is the impact of the intervention on the ground. So try to see, in terms of ecosystem services, what are the benefits from the conservation intervention. Then the multinational can report to their consumers and say, oh, look, we saved that much carbon. And that's the way also the multinational gain in the game, is to be able to show how much eco-friendly they are and attract more consumers. So basically, to do so, we need to project deforestation to say how much deforestation would have happened in the area if there was no intervention, and compare it with the actual intervention. So to do so, we create many models that basically calculate the risk or the probability of deforestation of all those pixels in the forest, and then put a risk level of deforestation for each of those pixels of low, medium, high. for each of those area, we will then calculate a rate of deforestation, or different rates of deforestation, and we will apply this then to feed some ecosystem services modeling. But just first, as an example, this is the protected area. This is the deforestation that is going on in the protected area. So yeah, even if it's a protected area, it still needs some conservation work, as we can see. We can see that there is different dynamics of change. So some areas are still well conserved with some degradation and so on. Some other areas already have intensified small-scale deforestation, and then you've got areas where there's even concessions that have been open for timbers and so on. So different rates and different dynamics in different areas of the protected area. And we model all of these through predictors like vicinity of roads, vicinity of rivers, and so on and so on. Then we use modeling in ecosystem services to assess different indicators in water provision, carbon storage, and biodiversity. And we mix all of this to finally compute what is the impact of the intervention. So here the impact looks quite small because we are taking all the reservoir of ecosystem services available in the area, and we compare it to what happened after 1 year of conservation. But the idea is that through time, you can continue to monitor those areas and show the impact that those interventions have had on the landscape. So this is basically to then have metrics that the private sector can share with consumers and so on, and say, okay, we are saving that much carbon, or we are preserving that much water for the local communities. And that's all. Thank you.
So hello everyone. My name is Juan Pablo Rojas, and I'm a PhD in the 3rd year. And I'm working on the analysis of point clouds, or in the processing of these point clouds of fruit trees in order to get the architectural traits of them. My topics in general are geoarchitecture, point clouds, and deep learning. So just to start, the objective of my thesis in general is to be able to extract the architectural traits from any fruit tree. And why we want to extract the architecture, or why the architecture of the tree matters. Because it helps us to manage different elements of the tree, like the tree pruning. Also, it helps us to understand how is the relation between the tree and the environment. Just as an example, I give the light interception. And also, it was shown in previous research that it has a correlation with the tree production. And why or how we process the point clouds, just to say that we wanted to analyze the point clouds because it gave us a high accurate description of the tree in general. But also we will see that when we have these point clouds, we will have the geometries are well deformed, and the densities around the geometries are very different. So this could affect how the model performs. And you will see some levels of occlusion in some of the organs. How we will start the analysis, just in the case of machine learning, we cannot just take the 3D coordinates that we have for each point and just do the analysis over that. We need to take a group of points and project them in some type of feature map. And just to know that there is PCL and other libraries that will help you to give this feature map from the geometry. After you can train any classifier, you can say that is SVM, random forest. And after you just have to do the tuning of this model in order to segment or detect the area that you want. In the case of the deep learning, so it's very recognized, and we just take the specific models, and the deep learning model help us to outperform or to extract the better features of the point clouds, and help us to segment the organ or detect a specific position. And to do that, just to know that each neuron is just representing like a small function, that a nonlinear function that can take several wakes and just give an output of that. Okay, just in my first results, or in the first year, I work mainly in the comparison between the aerial point clouds and the comparison of with the terrestrial ones. So initially, we have a apple color chart that is composed of 241 different genotypes, and each genotype is represented by 4 trees. And the way of how we do the experiment is that we have a line of 5 trees, and we do the scans, 4 scans for each of them, and after we merge them to have more or less dense point cloud. And in the case of the aerial scans, we just try to follow 3 protocols. The main variable that we changed in the flights, it was the speed of the drone. So we test 3 different speeds. In the first one, it's just 1 meter per second, and we set the height of the drone to 7 meters just to cover the specific area with at that speed. After we set the speed to 2 meters per second, and we just fly that at a height of 6 meters. And this was like a reference flight, like with this speed, and we can cover the area that we want. And the last one is just we have a flight of 4 meters per second, and the thing is that like we have a zigzag pattern in all the flights. In the last case, we just replicate 2 times that zigzag pattern because we have the double of the speed. And just to remark that the difference or why we do this is because we need to know that the terrestrial scans, they give you a high quality, but the problem is that they are too time consuming and you need a lot of effort to do the scans. In the case of with the aerial scans, you can cover a high area, more genotypes of the area that you want in a very short time. And you can, depending on the flight qualities, you can have different types of resolution of the data, sorry. So just to give you an example of the data, in the case of the terrestrial, the point cloud, you can see that the organs, the branches are more or less well defined. In the case of the flight point clouds, you can see that the inside of the tree is all the blue part is not well defined. You cannot see really the branches or other organs. So in order to process this data, it was proposed a pipeline that is composed of 3 modules. The first one, it's just in order to clean the data. It's in this case, in our case, we have the undesired elements like the soil, the pole, the water, the wire, and the other elements that we want to remove. And in order to in this model, it's composed of 2 parts. One, we use a classical method that is called Canupo, that is a binary classifier in order to segment the soil and the tree. And after we use a deep learning model that is called RandomNet in order to segment all the wires, the fruits, and other parts of the tree. For the tree clustering, it's because after you have the clean scent, you need to separate the trees in independent models, so you can after extract the indices. In this case, we use a clustering approach that is called label spreading. So we use as reference the coordinates, the GPS coordinates that we have of each tree. We put it in the cleaned point cloud, and we begin to spread that labels over the trees in order to know which cluster represent each of the trees. And finally, when you have the independent tree, you extract the indices. For the indices that you extract in general, where the alpha shape, the star, the convex solar radius, these indices, when we compare it with the 3 flights and with the terrestrial scans, we saw that when you have in general the volumetric comparison is the best correlation values that you can get. And after we also try with the convexity and the height, and we saw that there is some reduction in the correlation, and this happened due to the perspective of the scans. And also because the terrestrial will give you a high quality view of part of the tree, but from the top you will lose some parts of the tree and you will get some deformation. So for that, the correlation is reduced. We saw also that in the case of the editability, you will see some high values in the part of the terrestrial scan, and only when the point clouds are very low dense point clouds, in the case of the flights, you can have a different data. After, like we try to see, okay, now we see a general view of the tree. Now, how we can go more inside of the tree. So for that, it was proposed a pipeline in a collaborative work with Simon Arsat. In this case, the pipeline contemplates some the use of 2 segments of one that is composed of machine learning and the other one that is just a deep learning model. And again, we split it in 3 parts. That is the point characterization, the point classification, the point clustering. In this case, we just have the organ segmentation. And after that, I try to say, okay, how we can improve that organ segmentation. And we saw that when you start the model training from the scratch, like from random wakes, the model doesn't give a good segmentation of the fruits or the other organs. So we try to optimize the model using synthetic data that we create from a model that is called MapleT. And okay, we saw that when you do the, how can I say, the optimization weeks before the real training with the data that you want, you can achieve a better results in the classification, and it's showing the plots. So the index, in this case, the green bars represent the model that was training first with the synthetic data and after with the real data. And the red line is the one that was totally trained from scratch from the real data. Just to see that there is a small difference when you use the XZ coordinates or the reflectance values. We also saw that for these models, the most important features are the XZ coordinates. But if you want to improve the model, the reflectance and the deviation that you get from the LiDAR also give you a good description for the classification of the data. And finally, when we have the clustering, we just do optimization. We say that if a cluster is less than a few points, we will just start to merging with the closest clusters, and we get a good counting of the fruits in this case. After seeing that annotating the data for the deep learning models is very different, and seeing that actually there is a lot of processing in the part of deep learning, we try to say how we can use these models that were already developed for other researchers or companies in our project. So we try to say, okay, we can develop a GAN. That is like my last proposal for the thesis. In this case, we would say that we have the synthetic summer trees, and we want to approach in some way the distribution of the real trees that in this case. So we try to propose the merging of the models. One is called P2PNet. That is a deep learning model that was developed in order to project the shapes of different points. And after use PointNet++, that is just a classification and the network for general point clouds. So we try to optimize the two models based on the loss that we get from the discriminator that is PointNet++. And in our first results, that is something that is on the process, we try to approach just from synthetic data because it's the most easy thing to validate. So we try to convert from a winter tree, that is the tree that doesn't have tree or organs, to a ground truth, that is the summer tree that have leaf and other elements. But we saw at the moment my model is not able to converge or to project in a good way the organs. So it's a process, it's a work that is ongoing for the moment. Just as a conclusion, we have two pipelines that help us to count the organs of the fruit trees, that help us to extract general architectural traits. And also we saw that it's possible if you have your point clouds, you can approach with some indices the results that you have from the aerial flights with the terrestrial ones, depending on the values that you want to get. And that in the moment we have a GAN that is in the process of development. So, but I hope to end soon. That's all.